Hello everyone. So in this video, we will talk about the confidence intervals for the mean, for the mean with known variance. Okay, so when you know the variance, how can we construct the confidence interval for the mean? So what does it mean? What's a confidence interval? So I'm just giving a different way of defining the confidence intervals. So think about the hypothesis test. We said that the null hypothesis is mu is equal to 70 versus h1, mu is not equal to 70, okay? And using x bar, which was 71.8, right? And I don't know, but uh, for alpha is equal to 0.10, we just rejected the hypothesis, okay? So what happens if I just ask you, okay, with exactly the same setting, with exactly the same x bar, same alpha and same n, of course, n is equal to 100. What happens if we just test whether mu is equal to 71 or not? Or just test whether mu is equal to 69 or not, okay? So is there a way so that which gives you a kind of an interval over which if you make the hypothesis test, you won't reject the hypothesis, and outside that interval, you will reject the hypothesis, and that is what we call a confidence interval. Okay, we will give the exact definition, but for now, just you can think about the confidence interval as a shortcut for making the hypothesis test. So before finding the confidence interval, recall that x bar was normally distributed with population mean mu and with standard deviation sigma divided by root n. Remember, so if the population itself is normally distributed, then it follows that x bar is normally distributed. If the population is not normal, okay, then this still follows. By this I mean the normality of x bar, okay, normality of x bar, the normality of x bar, it still follows from this central limit theorem, okay? So, okay. Um, Now recall, we have for any standard normal, we have this, right? So this is standard normal where its center is at 0, okay? So if you just take an alpha over 2 from here and alpha over 2 from here, okay? So this is alpha over 2, alpha over 2. What is left is, let me just change the color. Um, your so the inside, okay, this shaded region from here to there, from here to there. So this is what? This is 1 minus alpha, right? And this this part is, remember, this is minus z sub alpha over 2, and this is z sub alpha over 2, okay? Um, okay, and so you can just write, remember, how can you just show this green region? This is simply probability that, this is simply probability that your random variable z, your random variable z is between minus z alpha over 2 and plus z alpha over 2. The probability that z is between these two values is equal to 1 minus alpha, right? So what I will do is, well, I know that x bar is approximately normally distributed, and hence this is standard normally distributed, which is equivalent to z, right? So x bar is normal, okay? X bar is normal. X bar is normal. This is its mean. I just subtract its mean, divide by its standard deviation. Hence, this is what? This is standard normal. Just plug it here, okay? Plug it here. So let's try to see what happens next. So this is exactly so this is the thing that we just plot in the previous slide. Remember this part, okay? This part, right? So if we just plug instead of the, if you just plug this part, this is what we have. And after some algebra, you can just write this, okay? Probability that your mu, remember what was mu? Mu was what? It was populations parameter, okay? Populations parameter, right? Populations parameter, and it was constant, right? Okay, and we don't know it. We don't know it. We don't know its value. Okay, its value. So the probability that the probability that x bar plus z alpha over 2 times sigma divided by root 10 greater than mu and x bar minus z alpha over 2 times sigma divided by root 10 smaller than mu, or in other words, the probability that mu is between these two values, that's equal to 1 minus alpha, right? So mu is in fact what? Mu is in fact in this interval. So this is x bar plus minus z alpha over 2 times sigma divided by root n, okay? So we can write the confidence interval as follows. So this is the formal definition, or this is the formal formula for the confidence interval. If x bar is the mean of a random sample, so in fact this s x bar, remember, when we just use small letters, it's the value, it's the scalar. So in fact this is x bar observed, okay? This is the observed value. If x bar observed is the mean of a random sample of size n from a population with known variance, sigma square, then 100 times 1 minus alpha percent confidence interval for mu is given by this formula, okay? Where, well, z alpha over 2 is the z value, which leaves an area of alpha over 2 to the right, okay? Again, note that, well, the value there is z observed, okay? So this is, sorry, this is x bar observed. So why do we have this different thing here, different mess here? So for example, if alpha, remember the alpha, it was the significance value. If alpha is equal to 0.10, then your confidence interval is 100 times 1 minus alpha, which is 100 times 1 minus 0.10, which is also equal to 90, okay? So this is percent, percent, and 90%. So alpha 0.10 means you have a 90% confidence interval, okay? So, right, recall our famous example, a random sample of 100 recorded deaths, right? In Turkey, during the past years show an average lifespan of 71.8 years. Assuming a population standard deviation of 8.9 years, please construct a 95% confidence interval. So since this is 95%, what does 95% corresponds to in terms of alpha? Alpha is equal to then 0.05, okay? So I need z alpha over 2, which is z alpha over 2, which is z sub 0.025, which is equal to 1.96, okay? Hence, the confidence interval is 71.8, which is x bar, recall, this is z sub 0.0525, sorry, 25, okay? And this is what? This is sigma, sorry, this is, well, okay, let me raise it like this. So this is z sub alpha over 2, and this is sigma divided by root n, okay? And I have a plus here. It's the same formula. The only thing you have a minus and a plus. And it turns out that the result is mu is between almost 70, okay, 70 and 73.5. So what does this mean? I am 95% confident that, or I am 95% sure that your your unknown parameter mu is between what? Is between 70 and, let's say, almost approximately 70 and 73.5, okay? So that's great. You don't know exactly where the mu is, but with some probability, with high probability, with 95 probability, you know that mu is between some value. In this example, it's 70 and 73.5. Hmm. Now let's think about, let me just, okay, we are 95% confident that our real mu is in this interval. So now let's talk about the 90% confidence interval. Okay, 90%. Remember the previous was 95%. So what do you think? Will it be, let's say, narrower? Okay, so let's say 95%. Is it narrower or wider? Okay, so if you are less now, I just want to make a confidence interval which is in which you are less confident with. Okay, so this should be narrower or wider. Let's think about this. If you want to be 100% sure, okay, 100% sure, sorry for this, 100% sure, then, well, if you want to be 100% sure, then your interval is something like this, okay, minus infinity and plus infinity. So what does it mean? You are sure, you are 100% sure that your unknown mu is between minus infinity and plus infinity. So if you just increase your confidence level, okay, let's say this is confidence level. If you just increase your confidence level, okay, then your uh, your interval becomes what? Wider. Okay, so interval just becomes wider. If you just increase the confidence level, then your confidence level becomes narrower. Okay, so there's a trade-off between the confidence level and the, let's say, and the length of the interval. So this confidence interval is now 70% 34, okay, 70% 34, and 73.26. Okay, let's compare it with this one. So this one is larger than this one, okay, and this one is smaller than this one, which means again, this is narrower than the previous so confidence interval. So, well, if you want more confidence, then the interval becomes larger and large. Okay, great. Now let's look at this diagram. So, well, what does this diagram look like? First, try to just pause the video for 1 minute and try to understand what does it look like? What does it say? What does it trying to say to us? Okay, just pause the video for a minute. Okay, so I guess you just paused and think about this. So just look at this one, okay? So let's see, this is, well, the x-axis shows the x bar values, okay? And the vertical axis shows the samples. Now what I have is, well, this is the first sample, this is the second sample, third sample, and so on and so forth. So at each sample, I have what? I have x bar 1, right? For the second one, I have x bar 2, x bar 3, and so on and so forth. And what I'm trying to do is just make a confidence interval regarding the using the x bars. Okay, so in fact, let me just erase this. Let me just erase this. So let me try to write the confidence intervals for each interval. So I have x1 bar, right, plus minus z. So this is the 90% confidence interval. Okay, believe me. So this is 0.05 times sigma of what? Sigma of x bar, which is sigma divided by root 10, right? So the second one, there is a confidence interval again. So this is x2 bar plus minus z sub 0.05 times sigma divided by root 10. Okay, so I won't write the third one because I don't have space there. This is x4 bar plus minus z sub 0.05 times sigma divided by root 10. So as you see, these parts are the same, okay? So these parts just show you what? So so these parts are the same. The only changes are x1 bar, x2 bar, and x4 bar. Now let's check here, okay? So this is what? What do you think about this? This is x1 bar, okay? How about this? This is x2 bar, right? This is x3 bar. This is what? This is x4 bar, okay? So this is x5, this is x6, and so on and so forth, okay? So how about this blue line? Well, the blue line is the, as you might expect, that's the confidence interval, right? So what does it mean? This part is simply z sub 0.05 times sigma divided by root n. Okay, that's great, right? So this is z sub 0.05 times sigma divided by root n, and the left part is the same as well. In fact, all of these parts, this part, this part, this part, this part, all of them has the same length, which is z sub 0.05 times sigma divided by root n. So what does this mean? It means that, well, here I have what? I have different confidence intervals, okay? So this is the so this one, let's say confidence interval with the first X bar. This is the confidence interval for the second X bar. This is the confidence interval for the what? For the fourth X bar, using the fourth X bar and so on and so forth. So what does this plot say? Well, it just shows you, assume that you are trying to make a confidence interval on the heights of students in the university. So this is the confidence interval. So this one is the confidence interval on the heights using the average of the first class, let's say some class in the school. This one is a confidence interval which is constructed by using the X bar of another class, of the second class, okay? So this is the confidence interval constructed by using the X bar of another class, the third class, okay, and so on and so forth. So there are 10 different classes. Let's say the first class is the statistics class, the second class is the production planning class, the third class is the electronics class, and so on and so forth. Also, all of them has the same sigma and same n, and these are the confidence intervals. So, okay, what's the catch here? So we say that, well, this is a 90% confidence interval, okay? So what does this show us? Well, this says that, well, 90% confidence interval means that you are 90% sure that your mu is in the confidence interval, okay? What does this mean? This means that, well, among 10 many confidence intervals, 9 of them will include, okay, will include the mu, let's say, but one of them will not include mu, okay? Understand? So 90% I am sure that this is my confidence interval means that, well, if you have, for example, 10 many confidence intervals, then 9 of them will include the real but unknown parameter mu, but one of them will not include the parameter mu. So if you just check here, look at this one. So this is the confidence interval constructed by the X bar of the 10th class. Does it include the real parameter mu? Where is the real parameter mu? It's here, okay? It's here, mu, right? So again, let me just, okay. So you see this, this is my parameter mu, okay? So does it include mu? Yes, it includes. This one includes. This confidence interval includes. This one includes mu. This one includes mu. This one, yes. This one, yes. The fourth one, well, the fourth one does not include mu, okay? So let me just check. Well, this part, it doesn't include mu, okay? And the remaining parts, the remaining confidence intervals, they include mu as well, okay, 1, 2, and 3. So it turns out that, well, 9 of them include mu, but one of them does not include mu, okay? So this is very this is another intuitive explanation of confidence interval. So if you just make confidence intervals with different data, for example, if you have a confidence interval, if you have a 90% confidence interval, it means that um, 9 out of 10 many instances you will have the unknown parameter mu in your interval, but in one of the trials you won't have the mu in your intervals, okay? A final remark is that, well, hypothesis testing is equivalent to confidence interval, okay? So in fact, this is the start of our, let's say, discussion at the beginning of this video. So just return to our hypothesis test question where we just test whether mu is equal to 70 or not, okay? So we can just draw the same conclusion by looking at the 95% confidence interval, okay? So here I have alpha is equal to 0.05, right? So if you just make this test at alpha is equal to 0.05, then just checking whether this mu is in this interval or not is equivalent to making the hypothesis test. Okay, so what does this mean? So 70, well, 70 is not in this interval. Okay, so let me just write it here. Um, Okay, so 70 is not in, let's say, 70.06 and 73.54. Hence, what you can do is you can reject H0. Okay, you can just so reject H0 at alpha is equal to 0.05. Okay, so if you just construct this confidence interval with this alpha, then with the same alpha, you can just reject the hypothesis of being equal to 70 since it is not in the confidence interval. So for example, if I just ask you what is the hypothesis test H0 mu is equal to, let's say, 71 versus H1 mu is equal, not equal to 71, mu is not equal to 71. Just look at the confidence interval. Is it in the confidence interval? Well, yes, it's in the confidence interval. Hence, you won't reject the hypothesis. Or if I just ask you H0 mu is equal to 73, for example, 73.5, let's say, H1 mu is not equal to 73.5, then do you reject the hypothesis? Just look at here. Well, not because it's in the confidence interval, so you don't reject this. So you don't reject this, you don't reject this, okay? You don't reject this. But for example, if I just ask you H0 mu is equal to 74 versus H1 mu is not equal to 74, will you reject the hypothesis? Will you reject the hypothesis? Well, it turns out that since 74 is not an element of this interval, the confidence interval, then you will reject the hypothesis, okay? So if you have the if you have the appropriate confidence interval, you can just make the hypothesis testing without making any further calculations. Okay. So what you can do is just write the confidence interval for 0.10 and try to make different hypothesis testing using that interval. Finally, we will talk about the error in estimating mu by x bar. Okay. So remember, for example, the real mu is here, right? Assume that the real mu is here. Let's say the real mu is 72. And so this is a point estimate, okay? So if point estimate turns out to be 70.5, then what is the error that you make? The error that you make is equal to what? 1.5, right? This is the error that you make. So since from the confidence interval you know that mu is between this part, this leftmost part and this rightmost part with what? With a given confidence level. You can say that, well, your error, which is this part, okay, so this is the error, this is the error, which is the x bar minus mu, let's say. So the difference between the real value and your point estimate. So the error is equal to 1.5 here, but with this confidence interval, I am confident that your mu is between this point and this point, which means your error with this confidence level will be smaller than z times z sub alpha over 2 times sigma divided by root n. Why? Because remember this part, okay, so let me just write this. This part is simply z sub alpha over 2 times sigma divided by root n, okay? And this part as well, this the same because that's symmetry. Z alpha over 2 times sigma divided by root n, okay? So I'm pretty sure that my error is smaller than this value with a given probability with a given confidence level. Hence, if you make some algebra, it turns out that uh, given a specified amount of error, for example, if somebody says that, well, just find me, I don't want the error to be larger than zero point 0.1, for example. If the error is given, okay, then you can use this formula to calculate the needed amount of observations to make the error as small as E, okay? Why is this important? Because, well, making an making an larger, okay, or making observations or experiments, okay, or experiments is expensive, okay. So what you do is you just want as small as possible. So you want n to be small. But if you have a small n, then what? Then your error will be larger. Okay. So what you do is you just first specify an amount of error which you can tolerate, then use this formula to find the required number of observations. So this is the end for this video. Okay.